So this is the outline of my talk. So I'll first recap the motivation and popular existing method for hypothesis tests in both for low-dimensional and high-dimensional inference for linear model. And then I'll explain how our method can method work in high-dimensional hypothesis tests with multiple responses for linear model. And after that, we extend our work to dimensional inference is in many scientific fields where we make a data set with much more features than observations. Which appears in biomedical researches, for example, gene data set, or finance, such as high frequency trading, and any field with modern sensor technologies. Those kind of data sets will have number of covariance greater than the number of observations. So, for example, in biomedical, if we try to figure out which genes really affect the cholesterol levels, then we may test 500,000 genes against like only a few few thousand observations. So it is a classic p greater than n case. So there are various methods can deal with those problems. For example, hypothesis test is one. Information criteria, for example, AIC, BIC, Bayesian post-theorem, we can impose a spike and slap higher and get the posterior of the indicator variable. This is another method. And penalize likelihood like lesser, ridge, etc. And our talk today, our work is focused on the hypothesis test. For standard hypothesis test, many methods, most standard method fail when p greater than n, because when p greater than n, the estimation become yield post. So let's formalize our problem setup. Let's consider a linear model first. So y equals x beta plus epsilon is very standard linear model. Y here is the response vector, x is the design matrix, beta is the coefficient, and epsilon is the random noise. So our goal is to test whether a subset of x has zero contribution to y. So we can denote the subset of x using, say, xb. So xb is our target covariance, and the remaining are called xa. So we can just call it a confounder covariant xa. So we can rewrite this linear model into this one here. And now our goal can be written in a mathematical way, say, what we want to test is whether the coefficient here, beta b, is zero or not. So in low dimensional setting, that is when p less than n, there is a few popular methods can be used for hypothesis test. All those one will be in our undergraduate case. So the first one is ANOVA F test. So basically, it is just the ratio between the sum of a regression sum of square versus the residual sum of square. Okay. So basically, what that try to do is the one on the denominator is the extra variation that xb can be explained, and the numerator is the variance that you cannot explain with using the full model. So y hat here is the estimate of y is under alternative hypothesis, and y hat a is the the estimate of y on the non-hypothesis. So you can basically think of this as a signal to noise ratio. So this is a signal and this is noise distribution. The second one is world type test. So this test is basically based on the likelihood, MLE, maximum likelihood estimates, the property of MLE. So we know that under regularity conditions, MLE, the maximum likelihood estimate, has asymptotic normality property. So with those asymptotic normality property, we can construct this test statistics. So basically, it measures how far your coefficient beta b from 0. Likelihood ratio test is basically the ratio between two possible best fit under non-hypothesis and alternative hypothesis. And the score test is basically using the fact that the score function, the expectation of score function under the true model is 0, and the variance is the inverse of Fisher information matrix. And also, we know that it has the score function has asymptotic normality property as well. So all those three methods are actually asymptotic equivalent to each other. So they approach to a chi-square distribution with degrees freedom of Q. So Q here is the dimension for beta b. But all those methods failed when p greater than n because of the yield-pulse estimation. We actually require that XA, that part is XA and X are full rank to be able to use all those methods. And this become impossible when p greater than n. And this also necessitates our new to invent a new approach for high dimensional inferences. So here, yeah. No. It's just it's the dimension of beta b. Yes. So now I'm going to introduce is for the high dimension. So what we discussed before is about the classical low dimensional method. Now I'm going to introduce 4 existing solutions to high dimensional hypothesis. The first those three can only deal with single beta b. So this is not a vector anymore. This is a scalar, and the one I'm going to introduce later, well, they can deal with the group hypothesis. So this beta here is no longer a scalar, it can be a vector. Okay, so those are the 3 methods I'm going to introduce. PDS, the post-double selection, and DS, and these specify the Lasso and the correlated score test. So before we dive into details about this high dimensional hypothesis, let's rethink about the problem of high dimensional test. So as we mentioned before, the problem is in high dimensional test p greater than n. But is that really because of p greater than n? If we assume that XA and XB are independent, p greater than n is actually not a problem, because if XA and XB are independent, we can regress XB with Y directly without XA. If they are independent, the estimate wouldn't be affected by omitting XA because they're independent, right? So now you can this high dimension test become a low dimensional, because what is being high dimension is this one. This one shouldn't be high dimension, but it is. This one is n times q. Q is less than n. That's what our assumption. Okay. So the problem is when P greater than N plus XA and XB are correlated. So in this case, if we omit XA and do the regression between Y and XB directly, the coefficient will be biased because due to the correlation between XA and XB. So the intuition here would be to solve this high dimensional issue. One solution is to reduce the dimension. The another solution will be to remove the correlation between XA and XB. So for this method, post double selection method, so what does it do is to reduce the dimension of XA directly. Very, very simple. The first step is regress Y on XA to select those subset of XA that really affecting Y. And the second step is doing the regression between those two. So you are finding the subset of XA that really affect XB. And then you get the union of those selected variables. So basically those two-step selection ensures that we don't omit any confounders in XA, and then do the least square regression. Like we can find the least square regression of Y using those two. And because this remains the same, but this one is actually the subset of XA, so it reduces from a high dimension from a lower dimension one. Then you can use standard method. The test statistics here is this one. Basically using with sparsity assumptions. We know that this one from the least square, this is the estimate from the least square regression. This is unbiased, and the variance can be estimated using least square standard error. It will be estimated consistently. So on the non-hypothesis, it should be a standard normal distributed. So this is the idea for post double selection. So it's very easy, but this is actually widely used in high dimensional causal inference. So the second one is despecified lasso, or called lasso projection. Different from what we see in PDS. So PDS is reduce the dimension of XA directly, but what they did here is slightly different. So what they did is still put XA and XB together to do a lasso regression. But what they did differently is we know that for lasso, the estimate is biased because of the penalty term. So it has a shrinkage effect. So the estimate here is biased because of the penalty term in the lasso. And what this despecified lasso try to do is to correct this bias using this correction term here. But how to correct this lasso term is the problem. So what they did is, again, regress XB on XA. This is like what they did in the previous method in the second step, right? And you will have the residual term EB. Because residual EB, this is the residual between XA and XB. So your EB here as a residual, it should be independent or orthogonal to this XA. And also on the non-hypothesis, we know that this term, residual without hat, should be independent to EB as well. Because EB here is, because the residual should be independent to X. If this, orthogonal to X, If it is orthogonal to X, it has been orthogonal to XA and XB as well. So this EB here, so the EB estimated here has double orthogonality. It is orthogonal to XA and is also orthogonal to the residual here. So with those double orthogonality property, we can find that the difference between the correct the Lasso and the true Lasso approach to this one here, and because those two are independent. When sample size are large enough, this one goes to 0. Okay, so here we correct. So what they did is to correct the Lasso estimate, and hence we can use, because it is now unbiased, we can use this Lasso estimate to do valid statistical inferences, and the variance can be estimated using those. So the variance for this one is quite straightforward. It can be estimated using this, and hence on the null hypothesis, it is standard normal distributed. So the idea here is account the correlation between XA and XB naturally using Lasso because they all fit together, but correct the bias later in this step. The third one, the correlated score test, it has very different motivation compared to the previous two, because the previous two, what they try to do is the test statistic is based on the estimation, but here for the score test, for the decorrelated score test, it is based on the score function. So the score function, as I mentioned before, it is also a quite classical method for hypothesis inference. But the problem in the high dimensional test is the component of score vector become correlated to each other. So due to this, due to those correlation, the variance can be distorted. So again, what they try to do is to remove the correlation between score function vector components, score vector components. The idea is also very straightforward, because we know that for score function, under the true model, the expectation should be 0, and the variance is the inverse of Fisher information matrix. So we actually know the covariance structure for lambda b and lambda a here. So this is the score vector. We know the correlation using the we can obtain the correlation using the Fisher information matrix, but this is only true when it is a linear model. So to remove the correlation, we can use this. And if we look into this one, what is that? It is actually the coefficient, the least square estimate for this, for the least square estimates between XB and XA. But the problem is here, again, this is invertible because this is not full rank. So what they did is, instead of using this gamma, they use a Lasso estimate. So basically what they did is you put another diagonal term, penalty term, inside this one to make this matrix invertible. So then they replace this gamma with Lasso estimates here to get a they call decorrelated score test. The variance can be estimated easily as well, and under the null hypothesis, again, this should be standard normal distributed. And as I mentioned, all the above methods can only deal with the single beta j, cannot deal with the group test. So we introduced the last one in the high dimensional test for linear model. It's called FHDI, the F test, high dimensional inferences. It is basically a residual based F test for high dimensional inference introduced by it is a work from Chong and group 2024. The idea is very similar to what we discussed before. We fit a lasso of y on xa to get a residual psi. You can think of this psi as a cleaned version of y after removing, after accounting the effect of xa, and fit another lasso on xb. This d is basically component of xb, so you deal it element wisely. And the residual here is you can consider this as a cleaned version of xb after accounting the effect of xa. Then you regress those two residuals. So you can consider this theta as the relationship between y and xb after accounting all the effect of xa. So this is a pure, you can think this theta as the pure effect that xb contribute to y. Now you reduce the high dimensional test to a low dimensional one because the dimension here is no longer p greater than n, is p less than n. And then you can use classical. Now it's a low dimensional one, so you can use a classical method to do the hypothesis test. So here we use the F test. They use the F test. So that's all the popular method, existing method. So now finally, what we do, what we did is to extend the work for multi-response. So here, y is no longer a vector, but it's a multi-response. For example, you have multiple phenotypes: height, weight, cholesterol levels, your eye color, whatever. And it's going to be a matrix. It's so that this is number of observation, this is number of phenotype. And X is the high dimensional covariant. N times P, you can consider this as genes. So P is greater than N. And again, our scope is to test whether this beta B is zero. So the traditional method to deal with single response, using single response approach, is to test those hypotheses individually. So what they did is to fit. Sorry, this is not M, but R separate regressions. So they did phenotype independently, but this will ignore the correlation, right? Correlation between those phenotypes. And joint modeling those phenotypes can boost the power to detect weak signals and also avoid multiple testing, because we know that if we test many times, we will inflate the type 1 error, and then to keep the type 1 error to be 5%, we need to do some correction, and then that will lower the power. So what we did here is we modeled them simultaneously to make it multi-response high dimensional hypothesis test. Again, I introduced some classical method because we're going to use those classical method later on. So those three methods are all classical popular methods in low dimensional multi-response case. Wilks lambda, they have this, Wilks lambda is basically the analog to likelihood ratio test in uni response case. So this E here is the you can consider this as the fit on the best fit on the that best fit on the alternative hypothesis, and the sum of those two will be the best fit on the alternative hypothesis. So this is the ratio of the two likelihood, and the Hotelling Lolly trace is basically the extension of F test, and the Bly trace is the extension of R squared in univariate case. But again, those methods can only deal with low dimensional case, namely P less than n. And on the non-hypothesis, those three methods has their own distributions. The first one is lambda distribution, and the second one is a combination, the product of two Wishart distribution, independent Wishart distribution. But for large sample size, those three methods are nearly equivalent and can be approximated by 1 on n chi-square with degrees of freedom R times Q. So R here is number of phenotypes. So it's from the dimension of Y, and Q here is from the dimension of beta. So beta B. So it can be approximated by chi-square with degrees of freedom R cube. But here I've got to mention that for Wilks lambda, it has to be minus log transit to make log transited. So lambda, lambda here is the, so if we look at this, so basically this is the ratio of this one. For the log likelihood ratio test, you need to put a log here. So okay, so now come to our work. Multivariate by this work, we extend the multivariate inference to the high dimension to the high dimensional and GOM setting using two-step residual refitting strategies. So again, this is the model, and this is the matrix. This is matrix. This is matrix, and this is matrix. So it is not a vector anymore. Our scope is to test whether this is the zero. Beta B is a zero matrix. Like what we introduced before, using in the first step, you will have two step. We'll have two regressions and to obtain their residuals, and then we regress psi on EBI. So basically, we look at this theta. So the reason why we can do that is we have this lemma. Under the linear regression setting, this theta equals beta B, and this eta I equals epsilon I. So what is this eta I? Eta I is here. This can, so with that lemma, what they try to say is, for this low dimensional regression, the theta here can recover the information of beta B, and this eta here can recover the information of random noise. So if we test the hypothesis on theta, it is equivalent to test the hypothesis on beta B, but this one is a low dimensional one. So now we convert the high dimension to low dimension. So from this to this, and we can use all classical multivariate test. So this is the three Wilks lambda, Hotelling P, and the Peli trace. So they can be all used because it is now a low dimensional one. But the problem is those are not observed. So psi here is the residual, right? The ground truth residual, and the P here is basically the projection matrix based on EB. This EB is this this EB here, they're not observed. So we need to estimate that. To estimate psi EB, we just fit R linear regression models on Y and Q linear regression on XB using Lasso. The Lasso can be chosen by cross-validation. Okay, so now we get the estimates, and the test statistics will become those one. So you basically substitute the estimated one with the ground truth replace the ground truth with the estimated one. We know that those three test statistics has good properties because people has proved that. But those good properties are based on the ground truth. So without this hat, without those hats, we know they all have good properties. But now we don't know what is the ground truth. We use the estimated one to replace those ground truths. Well, they still have good properties. And that's what we proved in our theorems. So under the null hypothesis and some regularity conditions, the test statistic Tn can be decomposed into those two terms. And if we look at this term, it is no longer the hat one, it is the ground truth one, and plus the small stochastic orders. So basically when we're saying when sample size are large enough, of course, P will grow with the sample size n, and we allowed, the condition here is log P divided by n goes to 0. So we still allowed P much more larger than n. So with those kind of regularity conditions, it can be decomposed with those ground truth one plus a smaller stochastic order. And the second theorem we proved is when sample size is large enough, again on the regularity conditions, those three test statistics will go to the true one when sample size is large enough. And we also proved those three are asymptotic equivalent to each other. So if we prove one of the one property, or if we prove the property for Tn, then for lambda, for V, they are all valid because they are asymptotic equivalent to each other. The third condition is the third theorem states it's distribution under null hypothesis. So we prove that this one goes to chi-squared distribution with degrees freedom R times Q, and we know that this epsilon is the random noise in the model. On the null hypothesis, this epsilon equals that psi, right? So we have shown before. So if this one on the if this one goes to a chi-square distribution, then on the null hypothesis, your Tn, we have proved that our Tn here, those terms here, should go to a chi-square distribution as well on the null hypothesis. And so that's what we state here. This is basically just saying we can guarantee the type 1 error here is alpha. Yeah. No, what? Which one? This one? Yeah. Yeah. No, because this is a low dimensional, so the projection matrix, so the E here must be full rank. So it will have. Yeah, because we assume that this Q here is less than N. So if Q that less than N is full rank, and then this is invertible. Yeah. Yeah. So theorem 1, 2, 3 is about the type 1 error, and this is about the power. So on the alternative hypothesis, again, regularity conditions, the leading term of the test statistics will be this one. That means the power depends on dB. What is dB? dB here is the true value of beta b. So if true value of beta b is not 0 and it is large, then the power will goes to 1. Okay, and this is a refined expansion. So basically, you can see that if we expand this a little bit more, we can see we have this term here, and this term is actually signal to noise ratio. So if the signal here is large enough, basically means the true beta b has relatively large signal compared to the noise, then your power goes to 1, will converge to 1. So that's all what we discussed above were all about linear model. The linear model is the simplest one. In many scenarios, your response is not continuous. It can be Poisson, it can be binary. So here we try to extend our work to generalized linear model. So the generalized linear model, Yij has this formula here. So it can be expressed using a exponential family. And the mu I here is the linear predictor, and beta b is the intercept vector, and b is the regression coefficient matrix. The generalized linear model will have conditional mean b dash mu I. B here is the canonical function, and the variance here can be decomposed in this way. So the reason why we decompose it in this way is because we want, at least for yi, here I'm no, not y, for each observation. So for y1, y2, y3, they have the same correlation structures. So we decompose into this one. So you can see you have a subscript I here, and those I, you have vi here, but this one is common for all i's. So we need to use this property to make that we can make some transformations to make y has a common variance. Okay? So we call this the scaled variance matrix, and bi is the conditional variance scaling, and we define the Pearson regression or Pearson arrow regression arrow, or the scaled regression arrow epsilon I as this term here, because we know the expectation is b dash mu I, and the variance is this one times tau, but this tau is common. That tau is common for all i's, so we don't need to worry about that one. We only need to scale this part. So all EI's will have the same covariance matrix, sigma, epsilon. So as I mentioned, our goal is still to test whether beta b is 0 or not. And we adopted the same strategy. Basically, we obtained the residuals from xi and from y and xa, and another residual from xb and xa, and we regress these two residuals. The only difference between linear model and generalized linear model is we need to divide by its variance, because for linear regression model, the variance is not consistent anymore. So we need to divide by its variance. Standard deviation. Okay, so here is the lemma. Unlike a linear model, there's a little bit drama here. So if beta b is 0, then your theta is 0, and your eta I is the epsilon I we defined before. But if your beta b is non-zero, like under your alternative hypothesis on non-zero, we can only say that your theta is not 0, but theta is not beta b. But again, our scope is to test whether it is 0 or not, but not to estimate what is beta b. So this is still reasonable. Again, we need to estimate what is psi I EB to obtain those test statistics. So we did the GOM Lasso regression to obtain all those estimates we need. Then about the theorem. So we have proved that all theorems from 1 to 4 apply to GOM case as well. So the only difference is we have slightly different regularity conditions. Especially in theorem 4, we can see the difference between linear model and GOM. So here it is exactly equal. It's equal. Here is asymptotically equal. But when sample size are large enough, it doesn't really count. So this is the theorem for GOM. Now, the last one, the Cox regression. So to make our work more complete, we have extended our method to survival data. So survival data present unique challenges. That is, your observation will be censored will be censored. So it will be possible that the observation is stopped before a patient experience a event. So we have, it is a censored data. So for the survival data, you have those set of observations. Ti is the minimum between Qi and Ri. So Qi is whether the Qi is time to the event. Ri is censoring time. So this is the Ti is the minimum of those two. It is the observed time. Indicator, delta I here is the censoring indicator. So if Qi less than Ri, it is means we really experience a event. So it is 1 and 0 means the time here is the censoring time. It is not the time to event. And the Cox proportional Hasse mode expressed here. And again, our goal is to test whether this beta B is 0. So we adopt the strategy from linear model and generalized linear model. We try to we try to use the residual to residual projection to test the hypothesis. But the problem here that the residual in GOM and the linear model is easy to define. Then what we should do to the residual of survival data. We had many tries, and then we choose the martingale residuals. So martingale residuals here defined as delta I, if you still remember that, is the indicator to say whether the event is, if event happened or censoring happened. And capital delta I here is the accumulated risk. So the difference here, you can think of it is the unexplained risk adjusted after XA. And this is actually a Poisson process. It jumps from 1 to counting process. It jumps from 0 to 1. So the variance is like a Poisson distribution. The variance is actually the equal to the expectation. So you can standardize this martingale residual or Pearson residual using this equation here. And the rest will be exactly the same. We obtain this residual and we find the relationship between this residual and this residual EB here. So this is second step. Regress the response residual psi on the target covariant residual EB. And instead of testing beta B, we are now again test this theta. here's the connection to the decorrelated score test in Van et al. 2017. And this method can only deal with a single response and single XB, like the individual beta J before. So the idea of decorrelated score is to, as we explained before, is to sort of remove the correlation between score vector components. So this delta gamma hat here is just the correlation, but it's the coefficient between XA and XB. Okay, we find our method has a close relationship to this method. So we prove that if on the null hypothesis and sample size is large enough, and those two estimates are consistent, then the decorrelated score function equals this one here. So this is basically because E hat is has mean 0, it's residual and must has 0 mean, right? Then this two is basically the correlation between those two residuals. Well, our theta here also measure the correlation between EB and the residual. But instead of the martingale residual E here, what we are comparing, or what we're dealing with is the standardized one. And we know that E is, so E hat here is a vector consists with like E1, E2 to En. And we know that they are not, they don't have a consistent variance because we have showed before this EI is a counting process, and they will have different expectations and different variance. This is the variance. So obviously it will be more sensible if we measure the correlation between those two using the one adjusted by its variance, adjusted by its standard deviations. So this is a more sensible way, and this is the relationship between our methods to the decorrelated score function. We haven't quite finished the simulation for the Cox Cox extension, but hopefully we can submit this paper very soon by adding this simulations result. So this is all about the method, and let's look at the simulations. Our simulations easy, and those 4 lines. I introduced 3 test statistics before, and there's another one. It's called Royal Max. All those 4 methods should be consistent to each other. And then this is the simulation for the type 1 error, and those 3 columns represent different way to construct the design matrix X. The first one is AR covariance, means autoregression. So the correlation between adjacent xi's, the correlation is rho. So here rho is 0.2, 0.7. The second one is block diagonal, means for a certain blocks, all x has the same correlation to each other. So here this means I separate this 200 covariance into 20 groups, and in each groups they have equal variance. This means I separate them into 40 groups, and each of them has common variance. And this one, equal correlation, means every all variance have the same correlation pairwisely. They are 0.2 and 0.7. It's the sample. Well, that's the sample size. Sample size. Oh, hold on. Sorry, it is not the sample size. It is the number. It's P. So sorry, it's Q. Q. Yeah. Yeah. It's the dimension of beta P. yeah, but for AR, it is around 0.5, 0.05. This is good. But for yeah, for this one, everything has same correlation, especially when correlation was large. Possibly slightly worse than others, but still reasonable. And this is the power. If power is like when here is the x-axis, here is the size of dB when your dB is large. So this is the simulation. And to conclude my talk, our method provide a unified framework to deal with the group testing for high-dimensional multi-response with mixed outcomes. So although when I introduced our method, we did linear first and GOM and Cox, but actually you can mix them together. Doesn't really matter, right? So your Y1 can be a continuous, Y2 can be a Poisson distributed response, and your Y3 can be a survival data. So you can mix them together, and you can still do the hypothesis test. And we post the quadratic form statistic based on the projecting estimation equation. And our method avoid estimating the correlations. So if you look at, if we look back to the steps we did, we never estimate the correlation between yi's. We did this regression separately, but still we will have this correlation between, because we measure this residuals. A residual will have their own correlations accounted in our quadratic form. And we allowed test different types of responses in one go, and it is valid under high dimensional case p greater than n, and the all test data follows asymptotic chi-square distribution under non-hypothesis. And also the good thing is because we did the joint modeling, it will improve the power of marginal test approach because we use the information about the correlation between y's. So it is sort of, so we can borrow the information between different yi's. So this sort of increase your sample size or increase your power. So again, our method has those theoretical guarantees, and simulation result for linear and GOM case at least works nice. I haven't done the Cox one, but hopefully the Cox will be okay as well. So this is all about my talk. So yeah. So